Hello, everybody. Welcome to the October Community Energy Lecture Series hosted by ASEP. Just like to thank everyone for coming out tonight. For those of you folks attending for the first night, I'd just like to let everyone know that this is a monthly event from September to May, except for December. We have a month off for the holidays. But this next coming November, we're going to have the folks from Cold Climate Housing come out, and they're going to talk about some low-energy housing prototypes, and that should be pretty cool. That'll be with Aaron Cook. Let's see. Tonight's lecture is going to run until 7:30, and then we kind of got to shoo everyone out the door because the Blue Loon runs a video here afterwards. So tonight we're going to have Carl Castle talk from Arctic Sun LLC, and just a little background information on Carl. Carl has a 38-year history in various management positions in Fairbanks, including public, private, nonprofit organizations. He has been a renewable energy hobbyist for more than 40 years, previously owned K2 Custom Construction, building high-efficiency homes. He has followed his family tradition and is a fourth-generation home builder. Carl is now the general manager for Arctic Sun LLC Renewable Energy Power Company. He also serves in the Borough Assembly. I'd also like to say that we're going to have Torsten Kloop come out tonight, but unfortunately, due to some schedule issues, he can't make it. But we'll go ahead and give it up here for Carl, and we'll take questions afterwards. So here's Carl.
Thank you, Max. Yes, Torsten was going to share the evening with me and do half of this program, but he's racing to the airport to go to Pittsburgh, where he's doing two presentations for the National Passive House Conference. So he wasn't quite finished with his second presentation this evening, and his looming plane departure was putting some pressure on him. So he just said, "Carl, can you wing it tonight all on your own?" And I said, "Sure. I can do that." Normally I'm talking renewable energy type items, and when I do talks on renewable energy, I always tell folks, before you get into the fancy technology things, what you need to do is focus on conservation, because the energy that you don't use is usually your best buy and the best bang for your buck. Saving the money up front, not using the energy, generally is cheaper and more effective. And so tonight, that's what we're going to talk about. And I'm not going to talk at all about the renewable energy end of things here. So, for the ladies who saw the Chippendale sign and pulled in, I'm sorry, that's not tonight. That's Friday night, okay? Please don't get me confused with that. This is just going to be about air tightness and energy efficiency. So the first part of the program, we're going to talk about the values and the possibilities and economics of tightening your home and the envelope to save yourself some money. And then as a result of doing that, you need to make sure your home is ventilated properly. And we'll talk about that and different approaches to how to get about that. So we're going to start at, say, 60,000 feet. And why we're talking about this is the buildings in our country use a significant amount of energy, of all the energy that is consumed. And of the building energy, you can see that space heating takes up quite a bit of that particular pie chart. Now, this is a U.S. national statistic where across the country, obviously, the average heating degree days are about half of what they are here in Fairbanks. So you would have to skew this, and obviously the space heating load would be significantly larger in Fairbanks than it is in, say, Denver or San Diego or somewhere in the lower 48. So the space heating component is obviously significant with the cost of energy. So how far can we go in saving energy? I really like this slide because I get upset with folks who think they're doing great and wonderful things with their house when they knock out about 5% of their energy load. This is kilowatt hours per square meter per year, and don't really worry about that. It's just, that's the unit that it's in. We're talking about energy here, whether it's BTUs or we're talking kilowatt hours, doesn't make much difference. So the average European home uses 134 units. The average American home is 130. We have a new building code for the United States that says to meet the code, you need to get your energy consumption down to 100. Then if you're doing really good and you want to go to a 5-star energy or a LEED type standard, you're down to 85. And my response to that is whoopee. That's just not good enough. That's not where we need to go. That's not sustainable. That's still an awful lot of energy. It doesn't even meet the current building code in Germany. A 5-star plus home here doesn't meet the regular building code in Germany. It doesn't even come close to the building code in Denmark. And it's nowhere near what passive house standards are. That would be my house or Torsten's home, or another half dozen that we've built here in Fairbanks. Look at the difference between 15 and a 5-star plus at 85. It's huge. And so, oh, I should have, okay. I should have, how do you get there? This is what you need to do to get to passive house standards. You start by maximizing the solar gain in the design of the home, and then insulate it to those minimum values, work on the thermal bridging to the best of your ability, eliminate, and with a little bit of work you can eliminate almost all thermal bridging in the walls. And what we're going to talk about tonight is this line: 6 air changes per hour at 50 pascals. That's the passive house standard right here. You got to do that or better. That's air tightness. That's how much air moves through the walls under 50 pascals of pressure. 0.6 air changes per hour. That's very achievable. My house, Torsten's home, is less than 0.5. I think mine's at about 4.8. His is about 4.2. And other homes that we've built are in the 0.4 something range. So it certainly is achievable. How do you get there? And why do you want to get there? Air tightness is the cheapest and easiest measure to conserve energy and assure the longevity of the core structure. If the wall is airtight and you're not getting moisture moving through it point loaded in one area, I'll talk a little bit more about that, you don't get mold and rot in your walls, so the sills don't rot out and your walls fall down. That's pretty cool. It also helps with health. We'll talk about more of that later, but focusing on minimizing the penetrations through the walls to the best of your ability. Don't go poking holes in your air barrier. Testing the system and retesting the system. And that's really important. A lot of contractors in town build homes, and when they're all done, they do a blower door test. Is everybody familiar with blower door tests? Do I need to explain that to anyone? I think most folks are on board with that. Okay. So you build the house, and then you do a blower door test, and you find out how good you did. Well, that's great, but if you didn't do so good, then what do you do about it? Because it's really hard, as we will talk here some more in a minute, to go back and fix things after the house is done. So you want to test the house while it's under construction before you put sheetrock over the walls or before you're covering up your air barrier in the wall so that you can't fix it. So you test it, you fix what you can, and then you retest it. And then you fix what you missed, and then you test it again, and then you cover it all up. And then when you get done, you can do one final test to see what you achieved. So, to get to the standard, you want to start with a good design for a continuous air barrier. And notice it says air barrier, not vapor barrier. There is a difference between the two. And we used to talk vapor barrier all the time, and folks are getting nervous to move away from vapor barriers and into air barriers. If you have a properly constructed wall with an air barrier, and by air barrier I simply mean to stop the movement of air through the wall through any pinholes or point sources. If the wall is breathable, and the analogy would be Gore-Tex compared to a Gore-Tex material compared to a waterproof raincoat type material, okay? Walls can breathe, and if they're breathing, just from the permeability of the material that they're made out of, you won't get enough accumulation of moisture in any one area in the wall to cause problems. And then the advantage of having a wall that actually breathes means it can dry out to the inside of the house or the outside of the house. The minute you introduce a vapor barrier to a wall, you're essentially asking for a little bit of trouble, because you can trap the moisture in the wall to where in the wintertime and when there's vapor pressure, you're pushing moisture through the wall. You push it into cavities. All vapor barriers are going to have little holes somewhere. We all know that. They always do. And wherever you have one, you will push moisture through that hole, and it will collect in that area in your wall. In the summertime, when things warm up and that frost or moisture that's built up in there during the winter from that pressure, there's no longer a big differential in humidity and temperature in the summertime, so there's no pressure to move moisture or air from one part of the wall to another. And if the wall can't breathe naturally and you've got this concentration of moisture and it can't dry to the inside of the house because there's a vapor barrier there and there's no pressure to push that moisture through the pinhole that it came in through, and you've got sheeting on the outside of your house which breathes and is permeable but at such a slow rate that if you've got condensed moisture in your wall, it won't have the opportunity to dry out during the course of the summer. And that causes rot and mold, mildew, and you've got structural problems in your wall and health issues, okay? So what we focus on now is doing an air barrier where you just aren't allowing the moisture to move through in pinpoint locations. And I'll talk about that a little more in another slide later. Whoops, let's go back to where we were. So you design for a continuous air barrier, and what that means is there is a plane through your wall, some layer that's continuous all the way around, so you have a solid envelope that is airtight. You make sure that windows and doors are all sealed properly, and you minimize the penetrations, as I said earlier, and then you test and retest, and you can get there with this. The standard we talked about for passive house was 0.6 air changes per hour. Alaska Housing and the Bees standard that they use, if you're going to qualify for Alaska Housing, their standard is 4 cubic feet per minute per square foot at 75 pascals, which equates to about 3 air changes instead of 0.6. So it's a looser standard, but yet this is tight enough that if your house is this tight, you're not going to get enough fresh air to be healthy. And we're going to talk about that. But you will be tight enough to at least meet the Alaska Housing standard for efficiency, okay? So how do we get there? Where does air come and go? Wow, houses leak all over the place. And air comes in and out. In the wintertime, it's pushed very heavily by changes in humidity. It's dry outside, it's wet inside. This is a bucket of water, essentially, in the wintertime because it's so dry. Moisture tries to equalize, just like water will drain out of a bucket if you put a hole in the bucket until the water outside the bucket is as deep as it is inside. Same thing happens with your house. The moisture is going to try to go outside, and it has pressure, just like water in a bucket has pressure. And it will push it through holes to get there, to do this. And so we also have movement by temperature and pressure differentials. So the air that's going out the top of the house, your nice warm air, is being replaced by cold air that's usually coming in the bottom, and the air rises because the warm air rises in your house. And so we get leaks all over the place. Real common bathroom fans leak around the edges. They also leak through the column itself because they don't seal closed very well. All vents, ductwork doesn't seal very well in Alaska. It's too cold. Attic hatches, always a problem. around uneven surfaces like chimneys, etc. And some people don't worry about things that leak into chases or gaps between ceilings. I don't know why you wouldn't, because it's just going to go into that space and then it's going to go out somewhere else where you haven't sealed because you were trying to seal this. Your air barrier was at the ceiling level over there. You got to think about all these different locations, all the penetrations, whether it's plumbing pipes down in crawl spaces going out. All these different areas need to be sealed up as tight as you can. And, you know, folks think, well, I'll just seal all these holes up. Back to the previous slides where I said minimize penetrations. Yeah, you can go back and try to seal these up, but it's way better to not put the hole there in the first place and try to seal it up, because where structures fail is almost always around patches that have been put on or attempts to seal things up. Real common to have those fail. So you need to look for all these places. If you're building a new house, you try to design them out from the beginning, like I was saying, and minimize them. And if you're working on a retrofit, because most of you probably already have a house, and you're scratching your head on trying to make it a little more efficient. And air tightness is the cheapest, back several slides ago. It doesn't cost a lot to do, and it has a huge advantage over other things as far as how much energy it can save. So bang for your buck, it is the #1 thing that you could do. So how do you find these leaks in an existing home? Well, a lot of times you just walk around and put your hand next to an electric receptacle and you can feel the cold air coming in. It's the easiest to do this the colder the weather is, because the bigger the difference of the temperature inside and out, the more the leaks are going to show up, because there's going to be greater pressure differentials from both moisture and temperature, and so you'll have the greatest airflow at those times. You can use smoke detectors like this. You can use a match and put it around where you suspect there's a leak. Frequently, you can just use your hand and find a leak. You can use infrared camera technology and take a picture. Infrared cameras tend to be kind of expensive, but you can buy a little infrared thermometer too that looks like a pistol, and you just pull the trigger and it shoots a laser beam out, and it'll tell you the temperature of whatever it's hitting, and you can scan it across the wall slowly, and you can pick up temperature differences like around this receptacle and see where you've got cold spots on the wall. Wherever you have a cold spot, if it's wintertime obviously outside, you know you've got a problem. You've got air movement there. Very typical locations, again, around receptacles, even though there's lots of kits out there for sealing up vapor barriers when you put in an electrical outlet or beforehand. There's a lot of different techniques. Those patches are typically where we see problems over a period of time. One of the reasons for this, if you think about it, it's kind of logical. When you're building a house and you're trying to seal it up, the person that gets elected to go around with the black goo and try to plug all these little holes up is usually not the boss, because that black stuff gets all over you and it's a real pain of a job. So here we have a task that's incredibly important to the detail of this home and its air tightness, and we're going to have the high school kid who's on his first summer job working with the black goo trying to plug holes up and whatnot. And so you tend to not get the highest quality job there. And yet it's one of the most important things that you can do with a home. So anyway, I'll get off of that horse. You also have a tendency to leak where vapor barriers are sealed in corners, like at the floor, at the ceilings, and where walls come together. And doors are particularly problematic. I think we all know that. So weather stripping for doors is very important. You can see the temperature difference here, 33 degrees to 60 degrees Fahrenheit in this picture. Real problem areas. Here's ceiling corners against a wall, and you can see we obviously have an air leak along the joint, and we also have insulation that's not tight to this rafters here, where this cold air that's probably coming in at this joint is bleeding down every one of these rafters because the insulation's not tight there. Challenging things to fix. Another ceiling wall and a skylight. Skylight's sealed pretty well on the sides, but the bottom along here, the whole structure is obviously leaking quite a bit. Very typical locations to see problems like that. If you go outside the house and look at it, you see the opposite now. The blue spots are good, and the warmer sections are the bad spots when you're looking from the outside. And it's pretty evident here. There's an interior wall that meets right here, and our air barrier didn't get sealed right in the corners. And so it's leaking significantly there. Typical problematic areas are where you have bay windows or pop-outs in an exterior wall, and frequently you don't get a good seal where the main wall pops out. So this is leaking quite a bit all along here, and obviously we're losing lots of energy in that location. So how much does this all add up to in the long run? Several studies. This one is on 10 apartment buildings, and the average energy use, air leakage is accounting for 14% of the energy that we're using here. What's more important in this slide is over here on the peak heat loss. This is when it gets really cold outside and we're losing heat the most. Now, what's it attributed to? And the air leakage is 24% of the equation when it gets really cold out. Now, this is a slide from the lower 48. So really cold means about 10 degrees. In Fairbanks, I'm sure, more than 25% you would find attributed to the air leakage because of the temperature difference. And so this is a big issue. If a quarter of your heat is leaking out or more when it's cold, I would think that that's significant. This is a totally different study. This is one individual residence, and this is the percent of air leakage going out in these different areas. A lot of people look at these scenarios, the studies, there's no two studies that were done alike, so it makes it hard to compare apples to apples from one house to another. But in this one, they're saying the floors and the walls and the ceiling joints are accounting for 31% of our loss. This one is one that I like to point out is 14% to the fireplace or the wood stove. If you have a wood stove or a fireplace, you really ought to use outside air into the firebox and run a line of pipe from outside into your stove for the makeup air that's going out the chimney. If you don't do that, you're using air from inside your house and you're pumping it out the chimney, and it's got to come in somewhere, the makeup air, and it's coming in through leaks around windows, doors, and elsewhere. And that accounts for 14% of your space heating needs in this particular house. The plumbing penetrations are significant. The doors, 11%. And ducts, because kitchen fans, bathroom fans, they don't seal up real good when they're closed and they leak, and you got a lot of energy going out there. Totally different house. This is, again, just one house study. What I found interesting, and I couldn't get from the article on this one, the doors are sieves. I don't know how many doors, though. So I don't know if we have one terrible door that's left wide open or if, you know, what's going on here. But the doors in this house were the big problem, and so forth. So how do we fix this stuff? We can use silicone caulk and spray foam. We can use foam strips, tapes. There's all sorts of different techniques. We can apply caulk around windows. Real easy to do. The physical part is real easy to do. Here we're just sealing between the window frame here and the brick wall. Pretty straightforward. Coming down the side of it, again, pretty straightforward. This is really the easy part. The hard part is trying to figure out where do we want to caulk. This is not easy. And if you go online, you're going to find a lot of misinformation. Here's some misinformation. We're going to caulk all these places here. Not if you're smart. You're not going to caulk all those places here. You are going to, whoa, wrong button. Let's back up. Okay. We are going to caulk here because this is where the window is meeting the rough opening window frame. So this is probably, and I am guessing a little bit here on exactly how this window was installed. And the next few slides we'll get into this a little bit more. But if we look at this, why do we want to seal the joint across here on the window trim? Is that really leaking any air in or out of our house? Because the air is moving all around behind this window trim. And so sealing it here isn't going to stop it from coming out along the edge over here. This is just window trim. This is just window trim. This may be a structural seam. I don't know how the window is installed for sure. This could be a good place to caulk. This probably is. This absolutely isn't. And so you got to look at how things are put together when you're trying to decide where you're going to caulk. Because how does air leave your house? Your air leaves your house through diffusion, where it can actually go through material very slowly and just seep its way through. We don't care about that. That's going to happen anyway, and it's no significant amount of money. So ignore that. We can have a hole that goes straight through. If we have a window that's installed here, and the space between our window and the rough opening creates a hole all the way through the wall, then we have this orifice flow or just straight through the wall because we have one continuous hole all the way through the wall. That happens a lot around windows and doors. They're notorious for not being installed properly. Both the rough opening to, in this previous case, the brick wall, there's a problem. And then inside the rough opening framing to the door structure itself can lead to another opening there. We also have what's called channel flow, where you got a hole down here like maybe an electrical outlet or receptacle. And so that's letting the air come into the space where you've got some fiberglass insulation. And like in some of those infrared photos I showed you, the air moves along the edge of that pretty well. It can move through it pretty well too, possibly. But anyway, just because it goes in here doesn't mean it have to go out right here. It can come up here and go out over there. So if you're trying to improve this structure, is that a good place to caulk? Can somebody tell me, is that a good place to caulk? No? Why is it not a good place to caulk? Yeah, okay, yeah. Yeah, there is that. And those are all good points. The real, and that's kind of a correct answer, because plugging it here isn't going to stop this at all. And it isn't going to stop this because this is going to go that way too. So we may slow it down a little bit, but the real question would be, where's the air barrier? Because back to this continuous air barrier we're trying to create around our house. If it is in the traditional old school, let's go back here. There. Let's go back here. All right. If it's in the traditional location, you've got a piece of visqueen or vapor barrier along here. That's problematic, and I won't get into too much on that. I mean, it's just back to what I said, there's always holes in vapor barriers. They're problematic, you know. You hang a picture on the wall and you poke a hole in it and then go ahead and try to fix it. Doesn't work, and you can't get at it without ripping sheetrock off. It's very problematic. But that's the traditional location for vapor barriers. So most of the homes constructed in Fairbanks, if they have a vapor barrier, that's where it's located. And so if that is the place that the vapor barrier is, that's the location that we've got to seal up, because sealing out here is going to allow all this channel flow to take place out through whatever holes. This is really where the building is leaking. That's where our air barrier is. In new construction now, frequently, if not most of the time, we have an air barrier out here instead of a vapor barrier, because we have a structural wall And then we have more insulation outside of where we have plywood and OSB or the sheeting on the outside of the house. There'd be more insulation here. This is a real good place to have an air barrier in a home, this whole length of this wall, because it's a very safe location. It's going to stay perfect if you build it perfect. You're not going to put holes in it. You can do whatever you want on the inside of the house. You can poke all the holes you want here, and you don't care about that because the air's not going to move through this wall. We're not going to consolidate a lot of moisture in it, and it can breathe in both directions doing that. So if this is the plane where your air barrier is, that's then where you want to caulk. And you want to catch all of them. So you want to catch this one as well as that one, obviously. But every one you plug helps a little bit. So, everybody with me on that one? All right. When you go online, you do get a lot of misinformation. Here's somebody telling you where to caulk your window. And I got to say, this is an opening casement window. We're caulking the opening window closed to the wooden sill. It's like, this is not where you caulk a window. And, you know, so you got to be careful going online looking for help on this. The key is knowing the structure of the wall, where the air barrier is, how the window was installed, where it's supposed to be sealed up, and stopping the airflow at that point. And it can be a real challenge, and it can be crazy expensive to really get to the proper location. You can also waste a lot of caulk trying to create some sort of an air barrier all the way around your window kind of deal. I discourage you from that because it really doesn't work. You need to find the places, and what it may entail, the places you're leaking, specifically in the air barrier, it may entail pulling off window trim on the inside to get at the joint between the frame, the rough opening of your window, and the stud wall. And I've seen so many houses where that joint is ignored because we're nailing two boards together, so it's not going to leak between them. Well, I'm sorry, it does leak between them, and that needs to be sealed up. And so it may not be as easy as you would like, but don't be foolish and just be doing crazy stuff like this either. You can also spray foam, great stuff, spray foam. And one thing with these, sometimes it's tough getting into tight places or getting all the foam out of the can, trying to operate it upside down. One trick is you can just take a straw and tape it on and make an extension and have a nice flexible straw to get you into tighter places and around corners. That helps a lot. And if you have a big job, you can buy more commercial size spray foam containers, and that's helpful for big jobs. And now we're looking for all the places that a house leaks. And we talked about plumbing penetrations are very common places that leak, and around plumbing vents that go up through walls and more plumbing. So you want to catch all of those holes. This is a ceiling that's going to get further insulated, but we're trying to stop the airflow around some sort of like a ceiling light, probably, recessed lighting. This is where an interior wall comes up. Probably not the best way to try to seal that, but it works too. So one tip on this too is when you're if you're gonna use spray foam for any number of repairs, try to get them all ready to spray at one time, because if you do one and then you have to prep the next area and you set your can down, the foam that's in it keeps coming out because the foam in the little nozzle will expand, and so you lose foam and it makes a mess and it sticks to everything, and you end up wasting some foam. So just try to get as many locations ready to go and save a little bit of your foam. So now that we've made a plastic bag and that we're living in because we don't have any airflow leakage around, is this really good indoor air quality to do that sort of thing? Because, you know, we breathe a fair amount. 1.6 while we're sleeping gallons we go through. And if you have any pets, dogs are terrible. Their respiration rate is about triple ours. So you go through a lot of air in your house, and that's a big problem because we've got tighter construction. We just made our house pretty tight, but also the number of chemicals and toxins that are in a home are significant, and some of them we don't even, I mean, they're getting new ones so fast we don't even know what all that they do. And of course, moisture and mold issues have gotten worse as we make things tighter, and all of the associated health issues with that. So if you really want health and comfort, living under a glass bubble or an airtight container isn't real good. It's not good for humidity control or carbon dioxide, volatile chemicals, as well as obviously smells and mold, all the stuff that we were talking about. And there's no pets in this photo, but I don't know, somehow this cartoon makes me cringe just thinking about recycling the air in a small space. And essentially that's what you're doing with your house when you get it nice and airtight. But you're going to save money if it's airtight. We'll talk more about that in a minute. And that's important. But health, I think, is ultimately important. I mean, it is to me. So no matter how much money I have in my pocket, if I'm sick or dead, it doesn't help me. So how do we take care of this? Well, back in the days, we talked about balanced ventilation, and you put in some bathroom and kitchen fans, and you blow a bunch of air out, and then you may balance that by having some supply fans that pump fresh air into your house, and you kind of try to balance all that. They talked about balanced ventilation. You may or may not try to put a heat source in here so that you're trying to warm this up a little bit, but you were just trying to get the fresh air into the house because you got to have it, and circulate air through the house by putting the fresh air coming into the bedrooms and the living spaces and pumping the old stale air and moist hot air out of the kitchens and the bathrooms. The basic concept with heat recovery ventilation is really the same as this. We still want to move the air in the same directions. The basis of it is good, but this eats up a heck of a lot of energy, and we'll talk about that a little bit more in a minute. So what we want to do is heat recovery ventilation or ventilator and supply fresh air and save energy at the same time. And it is possible to do this, actually. So with a heat recovery system, we're going to maintain our comfort and our health, and we're going to be energy efficient all at the same time. It's a win-win-win situation, and I've got numbers to show you that. But we end up with a healthy indoor, which is the most important thing in my mind in this whole equation. But I like the fact that it saves money too. So how does this stuff work? There's all kinds of different ventilation equipment out there, but a heat recovery ventilator, a quality one, uses a small amount of power by using DC motors. They're cheaper to operate, and you can move more air with a DC motor over an AC motor. And I got to say that back in the day when air exchangers, they were called when they first came out, they were nowhere near as efficient as what's available on the market now. We will talk about that as we go through this, but they started out with motors that used a lot of energy. They had poor designs, they had smaller cores, and we'll talk about all these different dynamics, but the efficiency wasn't very good. I owned my first one back in the late 1970s, and I wasn't impressed with it, and I was considering never buying one again because I was very unimpressed with the problems with it, et cetera, et cetera. And I got to tell you, we've come a long way since then. And one of them is DC motors now. In the higher quality units that are out there, they will save you energy. We also have the heat recovery unit, or the core, and that's the big shape here in the middle of this. That's actually doing the heat exchange from the outbound air, and we'll talk about that in another slide. There's also filters and combinations of filters that you can attach to these things. Like if it ever gets smoky in the summertime where you live, you can filter that out. And it just has a control display on it so you know what it's doing. So the core of this thing is the heat exchanger in the middle. And what we're doing is we're taking the inside air from the house and we run it through this core. Well, it comes down here and then out this side. The core is like sandwiches, different layers, and there's different types of cores. We'll talk about that a little bit more, but essentially you take the outbound air from your house and run it through core number or channel number 1, 3, 5, and then the incoming air from the outside of the house comes down and through here, and they pass each other because the outside air is between the 2, 4, 6, and 8, etc. Sheets within this core. And so passing by each other through the core, you exchange the heat from the household warm air, transfer that heat to the incoming air, and it ends up coming into your house much warmer. That's the concept. If you have a good unit, it also has a summertime bypass if you want, where you can take the air from in your house and just shoot it outside without going through the core and bring in the outside air into your house through it. So you're filtering the outside air coming in, helping to keep it fresh. And if it's hot in your house and you're trying to cool it, and you want to bring cool air in then in the summertime to cool it off, you can do that. And if it's a good unit, it is all automatic. It can do the summer bypass, and you can set temperature thresholds, and the little computers are so wonderful these days, the stuff they can do. It'll track all this for you, and it'll adjust the airflow one way or the other depending on how you have it set. And again, efficient DC motors, and continuously variable too, which helps if we want different airflow rates. I'm only going to mention this briefly, but an ERV is an energy recovery ventilator. It can be the exact same unit. The only difference is the core, and here's pulling the core out. The rest of this unit can all be identical, and it's just the core that's different. And in an ERV, you're not only exchanging heat, but you're exchanging moisture or humidity. So the plates in the middle, the membranes in the middle of the core here between the different flow is permeable to moisture. And so you can get a transfer of the moisture and help regulate humidity or keep it in your house in the wintertime if you want to. So with an ERV, you lose a little bit of heat recovery potential because some of the energy you're recovering is within the humidity and the moisture that's coming in. Overall, the combined energy savings between the two is essentially the same. It's just that the temperature isn't quite as good in an ERV, but it helps with the moisture humidity. So the only difference between the two is the core, which kind of core you have. And so what we're doing is taking our indoor air, and sorry, this is a German slide, so it's in Celsius here, 22 degrees inside. That air comes in the core and then goes through this way and goes out at 5 degrees. And the outside temperature right at freezing is coming in and going through the core this way and then into the house at 20 degrees. So we've transferred quite a bit of heat here. Not all cores are created equal. A lot of cores are just a straight line through that way and a straight line through this way. They're much cheaper to build. They're like those plastic signs you see that have the little holes through them, okay? So you put 2 plastic signs, or you stack up 50 plastic signs, and the odd numbered ones you just turn 90 degrees, and then you can blow air through one set of signs this way and the other one across them the other way. And you get heat exchange. The problem with that is then the amount of time that the air is exposed, the inbound and outbound air, is the distance from here to here. Obviously, that's a shorter distance than if we go this route. And so if the core has stamped panels with a longer channel, you end up with a longer linear distance for the air in and out to be passing each other, and you get a higher percentage of exchange with no more expense to no larger fan or anything else. The rest of the unit's the same. We just have better exchange in the core. And if you go to that kind of a core, you can get up to 90% of the heat exchanged from the air that's in your house to the air that's coming into your house. That's significantly better than opening the window for ventilation and having the air come in from outside at 40 below zero and your air that you've warmed up already going out and no exchange taking place whatsoever. Then you have to heat up all that cold air some other way, your furnace, your wood stove, or whatnot, and you have an energy cost associated with that. There's a big problem, let me back up again. There's a big problem with air exchangers that came out years ago. If you're dumping 40 below zero air into this thing, constantly flowing, got a nice breeze coming through there, and you're taking warm, moisture air going through the core the other way, the temperature in the core quickly decreases to freezing temperatures. You start getting condensation and the moisture starts freezing, and in a fairly short order your core is frozen. And when your core is frozen, you're not going to get any fresh air anymore. Now, depending on the model of your equipment, I won't call it it would be an air exchanger, I guess, back then, as opposed to a heat recovery ventilator, but even with some heat recovery ventilators, there has to be a strategy for preventing the ice buildup or getting rid of it. The two primary strategies are to go into recirculation mode, where you stop bringing fresh air in from outside and you take indoor air and cycle it through this unit until you thaw things out. Once it gets thawed out, then you go back to bringing fresh air in. That's fairly inexpensive to do, fairly. I mean, you're wasting all your fan power in the time while it's doing all of this, but you're also not getting fresh air while it's doing all of that. And when it's really cold out, it can be in recirculation mode for 2/3 to 3/4 of the time because it freezes up so fast. And so you're not getting fresh air for a significant amount of time while it's doing all of that. The other strategy is to try to warm up the air that's coming in. There's units that have electric heaters out here, so they take this cold air and they pre-warm it to some level with electricity, and there are others that you could tap it off of your hot water system or whatnot. But anyway, we warm that up enough so that it doesn't freeze the core, and we get better exchange. And that works, but there's a cost associated with that. You're spending a lot of energy. Most of them are electric, and electricity's not cheap, and it takes a fair amount of electricity to warm up 40 below air that's coming into this to keep this thing from freezing, because you got to change the 40-degree air to at least probably 28 or 29 degrees or so to keep the core from freezing. So all of that's expensive to do. There are some other strategies out there. There are units that have a ground loop like this. So we run very similar to a geothermal heat pump, okay, where you put coils in the ground to steal some energy from the ground. Except this is not a heat pump. All we're doing is putting PEX ground loop in and running a glycol solution through that ground loop and bringing that up into an attachment that goes on this ventilator. And there's a radiator in there that the incoming air goes through that radiator that you're circulating through these pipes, the fluid from the ground. Now, this is not like a heat pump where it's hot. We're just using ground temperature glycol, which is going to be about 38 degrees or so. But what it does is it warms up the incoming air just enough that it won't freeze the core. And that's pretty sweet, because in this system, the pump to run this ground loop as a DC pump, and it uses 7 watts. I mean, 7 watts is not a lot of power. And for that, we can run this ventilation system 24 hours a day at 7 days a week at whatever outside air temperature there is, and it won't freeze up. And we're spending 7 watts of energy is all to get there. So some of the improvements that have come over the years. So this is a real-life version of what we just saw a cartoon sketch of, installation. This is the HRV. This is the ground loop attachment with the radiator. This is the pipes coming in from the ground loop, and this is an auxiliary filter box system on this particular unit for cleaning the air coming in. This is a slightly larger version of it, and you can see these are the pipes that go out to the house, bring in the fresh air in. So the fresh air, we'll back up here. Here's our line coming in from outside, goes through and gets pre-warmed a little bit, and then goes into the ventilator, HRV, through the ventilator and out the other side and into a manifold box here, which then distributes that at equal pressure into each of these lines that run out to the house in the various rooms, bedrooms and such, where we're trying to put the fresh air. The lines over here are coming from the kitchen and the bathroom and taking the bad air out, and this box is another manifold on the other side. These are two separate boxes here, manifolds. And then that runs into the ventilator and out here and out this pipe and outdoors. Does this stuff work? Yes, this stuff does work. This is the money slide, so to speak. This is the one that you really need to know. So the red line is the outdoor air temperature, and down to about 0 at our coldest spot here, and up into the 40 aboves. Do your best to ignore these two blips, the blip there and the blip over there. That one was a equipment failure, and this one is some anomaly, I'm not sure exactly. But so we're going to ignore those two things for now. This is a 30-day history, actual testing of the system that we were just looking at. And so the air temperature is going up and down considerably. When the air that is going into this unit comes out of the radiator for the ground loop to go into the ventilator, that'd be the blue line. So here's the temperature that we're sending into our ventilator. This is, I'm sorry, I should back up. Here's where we really started. This was hooking equipment up, and so this is irrelevant. This line here is when everything was hooked up. And so the blue line is the temperature that we're feeding to the heat recovery ventilator. The light blue line at the top is the temperature in our house, and the green line is the temperature of the fresh air going into the house from the heat recovery ventilator. So we can see we've got about a 70-degree house temperature with the light blue line, and we're pumping fresh air in 24 hours a day, 7 days a week at 67, 68 degrees. This pump running the ground loop takes 7 watts, give or take 6 to 8. The DC fans on the ventilator are taking 12 to 16 watts is all. So for something under about 25 watts of energy, we're providing 67 degree or 68 degree fresh air 24 hours a day to this house. I find that incredible, personally. Impossible back in the 70s when these things first came out, but technology has advanced to such an extent that I find it amazing. 7 watts of energy are saving us this much from the red line to the blue line. Without the ground loop, this is the temperature that would be going into our air exchanger. So if you look at this space through here between the red and the blue, that's all of the energy that's being saved by running a 7-watt pump. And if we look from the blue line to the green line, that's the energy that's being saved by about 14 watts of power, because this is the air that would be going into the house without the ventilator, the blue line, but instead we're getting that 67-degree air into the house. And that air would all have to be heated by your boiler or some other source if you didn't have a heat recovery ventilator, if you're opening windows or whatnot. That takes a lot of heat to heat all that air. And obviously there's a cost associated with that. And this is much cheaper. We have found these numbers to pan out where we have installed these. Torsten's house has this exact unit, and he gets anywhere from 2 to 3 degree delta T, or temperature difference, between his house air and the incoming fresh air out of his unit. And I find that pretty sweet. Looking around the world, trying to get some more research on this, there was a study done in Switzerland. This has a variety of different fun things. These were very green homes that were built, designed, and tested and modeled. And the research that was done on it was to try to get to net zero. And I won't talk too much about net zero, but I do want to talk about this slide a little bit. What we've got going on here is this is the average home in Switzerland and the amount of energy it uses, and we're going to upgrade different things in this. That's what this project did, and see how much energy could be saved. And so when we did some part of the model, we saved some amount of energy. The effect of the measure is the dark part of each one of these graphs, and then the lighter part is what's left over to try to achieve. So we took the average home, and we changed the shape a little bit and whatnot, and we saved a lot of energy just by changing the shape of the building. And we've talked about this in some of our other presentations we've done over the years. Not a big point for tonight, though. Orientation of the windows, just moving some things around a little bit helped us. We got better windows, better U value or R value, and we saved this much energy. And then we insulated roof and walls a little bit better, and we saved some more energy. And this was over the existing average in Switzerland, which was already pretty good, so this would typically be larger. But then we got down to the HRV, and by putting an HRV in, as opposed to not having it, that's the only change, we had this much of an effect, difference, in the energy consumption of the house. Pretty significant. And it was one of the no-brainer things that they said to do. The other items that they have were more questionable for a variety of reasons, and I won't go into that tonight. But the bottom line is the HRV was something that they said was very important, and you can see it saved a significant chunk of energy compared to a lot of the other things. It certainly is something of value to be thinking about. So then in Finland, they did a study. This was a much larger study, and they looked at, I don't know how many thousand homes, and they came up with an average kilowatt-hour heat consumption, 29,000. Not too bad, actually. Better than here. But by comparing that to the same homes with an HRV, they saved, the number that I like is 15% of the space heat requirement by having an HRV. Saved 15% of the energy bill. So looking over history, this is how we used to ventilate. Bathroom fans, kitchen fans, turn the fan on, get some air change going on, blow a bunch of air out, and it'll come in all the holes in the walls, and we have fresh air, and we got rid of the stinky stuff. That had a cost associated with it. We had to run the fan. That used a little bit of energy. Then we had to heat all the air that came in, because we brought all this cold air into the house, and we blew all the warm stuff out. If we look at running this fan, our bathroom fan, you wouldn't do this, because you'd go broke, for one thing, but running the fan, if you are maintaining 70 degrees in your house and it's 30 degrees outside, that's not minus 30, that's 30 degrees Fahrenheit. If you're running your fan 24 hours a day, you're going to go through 62,000 BTUs a day. That's our column here. If you just use your fan when you have to for a couple hours between the kitchen and bathroom fans, you're still going to have an energy drain out of the house that comes out to 10,000 BTUs. Fairly significant. There's three factors that we've been talking about with ventilation and air. One is the energy end of it. One of it is the health aspect of it. And one of it is comfort. And comfort here is we're bringing cold air into our house at 30 degrees all over the place. Who knows where it's coming in. Even if we have a makeup fan that's bringing it in through designated vents, the air that's coming in is at 30 degrees because that's the outside temperature. And Have you ever been in a drafty house in the wintertime and you don't want to be sitting next to where that fresh air is coming in because it's fresh, it's refreshing, and it's kind of cool. So the comfort level goes down. And so if you look at these two options here, this one's probably really healthy. This one's probably not healthy. This one isn't using too much energy, so it's good from the energy equation. This one's terrible on the energy equation. You're going to go broke doing this. And neither one is too good from the comfort level. So let's look at some options. Let's use a fairly inefficient heat recovery ventilator. This one's 75% efficient, which is what most of the standard kind of HRVs in the market, even today, really, to tell you the truth, a lot of them are in that range. 75 to 80% is fairly common, okay? So we do the same thing. We can ventilate for 24 hours a day, and with this particular unit, we're going to save a lot of energy at this efficiency level, even factoring in the energy that the unit's using. We're still not doing too bad here on that. We're getting 24-hour-a-day fresh air, so we've got health going for us. And over here, we're doing much better on the comfort level because the air that's coming in is at 60 degrees. We'd like it to be 70, but okay, it's 60. And that's not too bad from a drafty kind of a scenario with it. So we're not too bad on it. Well, let's see what happens if we get a little better. Let's go to 90% efficiency, which the top-of-the-line models will actually do. And these are available today. We'll run it for 24 hours a day, 7 days a week, and it's going to use 6,000, or the efficiency level will have a cost still of raising that fresh air. So we've got health going for us. We've got 24-hour-a-day fresh air. We're not using much energy in the equation, and our comfort level is pretty darn good. At 66-degree air coming in, you'd hardly notice the difference unless you had your head stuck in the vent. So this is the kind of numbers that have proven out on the testing on all this equipment, laboratory, yada, yada, et cetera. And I'm kind of liking those numbers myself. And from our experience with what we're doing, all of these are absolutely true. The research that we've done here in Fairbanks indicates exactly the same from the unit that we have in Torsten's house. And actually, we've installed a few others. We don't have as much scientific tracking on the other ones, but the tracking that we do have confirms all of these numbers. So over time, this is what's been going on. Our comfort in our homes, the red line, has been getting better all the time since back in the 1950s. We first started doing it by throwing tons of energy at it, this line, and then we figured out that that wasn't sustainable. We were using too much energy, and so we came up with more insulation and did things to bring the energy line down on it. We're getting better with construction techniques. They were going up in cost, and now we've hit a spot where we're actually being able to build some of these systems a little bit cheaper. Things are going to keep changing. Change always happens. We hope that we can keep improving comfort levels of homes. It takes all of these different things to do that, and as technology gets better, just like with the HRVs, I'm 1,000% in favor of a high-quality HRV today. I wasn't with the first one that I owned, and I almost never bought another one, but I've seen the progress over the years with them and have seen the savings. There's other fun stuff, too, going on. Living walls, I kind of like these. We've done a couple of these. They're kind of fun. You can do them at any scale, large or small, but a good way to get some fresh air. I really like this, just using a fan to pull air through all of the growing plants on the wall and up and out, and you're blowing clean air into the house. So this is just an air cleaner is what it is, an air filter. And you're getting fresh air at the room temperature because this is just room temperature air going through the whole system. And circulating water from the catch here up and letting it drip down through the plant medium. Kind of fun stuff. So with that, I guess I would say thank you, and do we have questions? Because I'd be glad to answer questions. I'm sure I missed a million things. Yes?
So I just had the interior weatherization come to my house, and they put in a heat exchanger, and the box is like this big. I don't know what kind of heat, if it's an HRV. I don't know what it is. Do you have any idea?
I can't quite see it from here. I would say, if they said it's an HRV, yeah, if it's some sort of heat exchanger, it's some kind of an HRV. And it probably fits somewhere within the range of the numbers I was showing you, from the 75%, although there are actually some that are not even 75% efficient, you know, up to potentially 90, 92%. That's the upper limit of efficiency on these. So I don't know where it fits in the scale of things. I would be suspicious not at a unit that size would not be near the top end of the scale. The variation on these can be huge because, like most things, you can solve problems by throwing more energy at it. So you can use small boxes with less efficient filters and just put a bigger fan on it and drive more power to it. That uses more energy. And so we're trying to balance the energy equation here. If you're gaining 100 kilowatts over here on the heat that you're saving, but you're spending 100 kilowatts over here to make the system work to save that 100, you haven't saved anything. And so you got to take a close look at the energy that your equipment is using on this side of that equation to see how much you're saving on the other side. And so what we have found is a lot of the older models were using 200 and 300 watts to get a 75% efficiency on the other side of the equation, and they were barely balanced as far as from an energy perspective. You weren't saving any money, really. You were addressing the health issue, and you were getting fresh air, which was good most of the time because they were prone to freezing up. But you know, they just really, there was a real question as to whether they had the value and were worth doing it. But now, with the better models, they absolutely are. If you do your homework and find a good one, you will find that it's going to use a lot less energy, cost you less to operate, and you can get a higher percentage return on the energy that it's saving from the outbound air from your house. And the volumes of air we're talking about it can be very significant. And then it maintains an even pressure in your house and decreases the amount of air that's coming in through these various air leaks, et cetera, in your house also. So there's other ripple effects of benefits from it. What other questions do we have? There's got to be some. This is such a huge topic.
When you use that ground source, how deep do you bury that and how big a pipe?
Just takes a small pipe. The question is the ground loop for the attachment on the HRV. How deep and whatnot, the specs on that. It's just a small PEX tubing, 3/4 inch, 5/8, depending on which model you're using and whatnot. We recommend 400 linear feet to maybe 500 linear feet of it installed in the ground. If you're doing a new house, the trick way to do it is when you go to put your septic system in, you dig the hole for the septic system and you throw the pipe in the bottom and then just build the septic system over the top of it. It doesn't pull enough heat to freeze up your septic system. You get a slightly higher ground temperature there, and you haven't wasted any money digging a hole to install the stuff, because it needs to be at least 6 feet down, preferably a little bit deeper than that if you can. The deeper you go, the better. But if you're digging a hole specifically to put the pipe in, because it's a retrofit and your house already exists, and you're digging a 400-foot-long trench, you're probably only going to want to go 6 feet. I mean, that's the significant cost associated with that if it's a retrofit. On a new construction, it can just go around the house like that picture showed. So when you do the excavation, just before you start backfilling around your foundation, you lay the pipe in there and then backfill, and that saves money too. Like most things, the installation cost can be significant one way or another depending on how you're doing it. Yeah?
Are there good ways to integrate HRV with an existing forced air heating system?
That's a tricky game to play. Normally, I think you'd really want to keep them separate because you're going to balance the system and get everything working properly. I think there's too many variables to try to combine it. You could dump the air into your existing ductwork and utilize ductwork that you already have. That's a problem on retrofits with any kind of an HRV or ventilation system, is you need to get this air moved around the house, and you're trying to take it out of bathrooms and bedrooms and put it, or bathrooms and kitchens, and put it into bedrooms and living rooms and such. That may or may not be easy to do depending on the floor plan in your house. Regular metal ductwork is really hard to retrofit install. That's one advantage of this particular model that I was showing you, these Zender units that we're importing from Germany. They're available in the United States now, but the ductwork is those hoses that you saw, and they're sized where they can fit in a 2x4 cavity. They're just under 3.5 inches, and so you can run those vacuum hoses essentially through the walls a lot easier without tearing your whole house apart. So it is a big step forward from that perspective. It still isn't perfect because you still got to get the ductwork from point A to point B, and there's challenges depending on the structure of your home and the floor plan, et cetera. But one advantage of these is you really want to be able to clean them too if you can, and if you've got rigid 90-degree corners in sheet metal ducting, it's really hard to get those cleaned out, whereas with a tubing like this you can just run a pipe cleaner type through the whole thing and snake it all the way through from one side to another like you're doing a sewer line. So anyway, did that answer your question? I rambled there a little bit. Other questions? Yes?
How would you know how to size a green wall and still have the same effect as an HRV did?
Well, the green wall doesn't have totally the same effect. It cleans the air, but it's not exchanging air from outside the building, so you're not quite getting the same kind of a ventilation change that you would with an HRV. And sizing it would be, kind of, it would depend on the fan. There's just so many variables. I think it would be a challenge. I think just taking a kind of somewhat educated guess to the size, comparing it to the size of the house and what your air demand is, how many people were living in the house, how much respiration did you have going on, what other plants were available. You'd have to weigh all of that and kind of guesstimate where you were going with it. But they've done a lot of big ones in schools and commercial buildings, particularly in Europe. There's a bunch of them, and they love them. I mean, they say you can really tell the difference in the air quality from the rooms that have one to the rooms that don't, in the big public areas of these buildings. It's quite noticeable. And I imagine it would be. I mean, when we walk through the woods, you can just smell the freshness in the air and whatnot.
So would they typically combine it with an HRV then?
Typically, yeah. You might downscale the size of the HRV or throttle it back or whatnot. But yeah, typically you'd combine it with another ventilation system. I think maybe in a small residence with one or maybe two people, it wouldn't be as important, but I think, fresh air is just an absolute necessity for us. We go through a lot of it. And hopefully we can keep going through a lot of it, because when you quit using it, you got a big problem on your hands. So, I mean, it's important to life. We need to take care of it. And it's my top priority. Yeah?
Is an HRV system feasible in a large, warehouse or hangar building?
Oh, absolutely. Yeah, they come in all sizes. There's commercial sizes, residential. There's like 3 or 4 different sizes just specifically for residential homes. So, talk to a reputable dealer and they'll size it and tell you, what size you need for your specific application. Big part of it's the square footage of the house, but also the lifestyle of the occupants. A lot of this stuff varies, it's site specific, and part of the site specificness is who's living there and what are they doing inside the building. What's their lifestyle, how many pets do they have. Those kind of things make a big difference. And so you can size it to the building and get close, but what's going on inside too. Yeah.
And if you had a resident affiliated with a large warehouse, would you use 2 units, 2 separate units?
No, not necessarily. It depends on the volume and whatnot, but what you do is, particularly with this kind of the Zender model was the model that I was showing you most of the pictures of, you can adjust the flow rate to the different areas by how many ducts you run and how it's ducted, so you don't have to have the same capacity to every room in the building. You adjust that. And we model that for you and make recommendations for what you would need in each room and design the whole system for you and work with you on it. You can do it yourself too, but we do it for free, so might as well let us do it for you. Other questions? I really appreciate your time for coming out and listening to me ramble on. I think this is good stuff, and I think it's important for sustainability and healthy living. And you know, we're on the edge here in Fairbanks in one of the most extreme environments on the planet to try to live. And every little bit we can do to save energy saves us money, saves the planet, and makes all of this a little more sustainable. So I'm glad you're interested, and I'll be around too if there's other questions that come up, and thank you for coming.